is experimental study on strength properties of landfill liner material with inclusion
Şerife,
of polymeric
tamam,
fiber. Waste disposal becoming one of the most serious prevailing environmental problems in developed and developing countries all over the world. Wastes such as municipal, industrial, mining, nuclear, and packaging byproducts accumulating in landfill areas generate contamination, imposing detrimental health and environmental problems. Landfill barriers, liners, and covers are widely used in the waste containment facilities. Aims and scope. Assessment of mixtures of soils in different combinations to be proposed as possible landfill liner materials in a semi-arid climate. Cost-effective materials are considered, which are locally existing soil types and some industrial wastes for additional improvement of the selected soil mixtures. Industrial wastes are used to enhance the hydromechanical properties of compacted soil mixtures as well as to create a recycling option for the undesired waste. Expansive soil and beach sand are used in this study, and the waste product obtained from the construction industry is the polyvinyl chloride pipe cuttings. Polymeric fiber reinforcement. Utilization of plastic waste became very popular due to technical, economical, and ecological reasons. In addition, they enhance some engineering properties of soils. To improve the ductility and strength of stabilized soils, mainly as road base subjected to traffic loads or landfill barriers, there is an increased usage of plastic waste materials as a secondary additive. Here we can see some examples of plastic wastes, which are polypropylene plastic sacks, plastic bottles, polyvinyl chloride pipe scrap, and rubber waste. In the literature, researchers worked with different types of fibers such as polypropylene fibers, polyester fibers, coir fiber, carpet waste fiber, and nylon fibers. Various researchers investigated the effect of fiber on strength properties, but limited studies have been conducted in which fibers are used as additive in expansive soil sand mixture. The research herein focuses on the combined effect of sand expansive soil reinforced with randomly distributed polymeric fiber on the strength properties. Strength properties were analyzed with unconfined compression test and flexural strength test. Materials and soil groups. Expansive soil, beach sand, and polymeric fiber are used in this study. Expansive soil was obtained from Nicosia, and beach sand was taken from Famagusta coast. Expansive soil is classified as silt with high plasticity, and beach sand is classified as poorly graded uniform sand according to the Unified Soil Classification System. Polymeric fiber was obtained, it was collected from a pipe manufacturing factory, which is a waste material produced in the form of varying size, thin and soft flakes during the cutting process of PVC pipes. We can see the polymeric fibers from these two pictures. They are thin and soft flakes. Normally, for the polypropylene fibers, their aspect ratios are mentioned. As we know, aspect ratio is the ratio of width to height, but here in this polymeric fibers cannot be determined due to their irregular shapes and sizes. Soil groups. There are 4 different soil groups. Our control soil is NS. We named as NS. It is 50%. It includes 50% expansive soil and 50% sand. And after that, we added polymeric fiber with 3 different percentages to the control soil, which is NS. And in each soil group, expansive soil and sand, they are in 1:1 ratio. Experimental results. Before starting to check the experimental results, I would like to mention that in this study, compacted soil samples were used and they were prepared in their optimum moisture content and maximum dry density values. The first strength test is unconfined compression test. Unconfined compression test applied on all soil groups, and after performing the test, the stress-strain relationship was obtained. The stress is the compressive stress and this is the axial strain, and we can see the change of the curves after the polymeric fiber addition. And in the second figure, it shows the influence of fiber content on the failure strain. In the second figure, we can see the failure strain versus fiber content. And when we check this figure, we can see that the failure strain it increases with the inclusion of fiber content up to 2%, and after that it starts to decrease. The unconfined compressive strength and the failure strain values are listed in this table. So we can see the unconfined compression test results in this table. Let us start with the unconfined compressive strength values. So the unconfined compressive strength is observed to increase slightly with the addition of 1% polymeric fiber, and it shows a slight reduction with the inclusion of 2% polymeric fiber, and when we add 3% polymeric fiber to the expansive soil sand mixture, unconfined compressive strength decreased. So it means here we don't have any significant improvement in the unconfined compressive strength. But on the other hand, we should check the failure strain because it is important in the ductility behavior. So when we compare the failure strain by checking these values, we can see that the failure strain increased with the addition of polymeric fiber. But here, when we check the results carefully, we can see that the failure strain of NS it increased by almost twofold with the inclusion of 2% polymeric fiber. Therefore, we can say that utilization of 2% polymeric fiber has not provided an improvement in compressive strength, but it caused the material to become more ductile. Therefore, 2% polymeric fiber can be selected as an optimal value. Flexural strength test. Flexural strength test is an indirect method of tensile strength determination. Tensile strength is important and it is required in the studying of highways, landfills, and airfield pavements. Stability and toughness are the two important parameters for pavement materials to prevent sudden failure after peak due to the traffic load. In this test, beam soil specimens were used, and the flexural strength is calculated by using this formula. F is the flexural strength. It equals to 1.5 times PL over B times D square. P is the flexural load. L is the span length. B and D are the dimensions. They are the width and the depth of the beam. Here, after performing the flexural strength test, we obtained the load deflection curves, and after calculating the flexural strength, in the second figure, it shows the flexural strength versus fiber content. We found some parameters from the load deflection by using the load deflection curves. And if we look at the second figure, it is clearly seen that only 2% polymeric fiber inclusion increased the flexural strength. At the beginning here, we don't have any polymeric fiber inclusion. And when we added 1% and 3%, as you see from here, the flexural strength decreased with the inclusions of 1 and 3% polymeric fiber. Toughness is another important parameter, and toughness is the ability of a material to absorb energy during fracture. And we can find the toughness again by using the load deflection curves. Toughness is the area under the load deflection curve from origin to the target deflection, which is L over 150 millimeter. Flexural performance data, all the parameters which are obtained from the flexural strength tests, they are listed, they are summarized in this table. Let us check them together. Here we can see the soil groups. P1, it is the initial peak, and it is also known as the limit of proportionality. PF is the peak flexural load. PF over P1. Here, if these two loads are almost equal, so the flexural behavior is deflection softening. If this ratio is greater than 1, the flexural behavior is deflection hardening. F is the flexural strength. FD is the residual load at deflection of L over 150. T is the toughness, and RTD is the flexural strength ratio. After obtaining the flexural strength ratio, we can also make another comment. If this value is less than 100%, deflection softening occurs, but if this value is greater than 100%, deflection hardening behavior occurs. By checking all of these parameters, the flexural strength ratio, toughness, and the flexural strength values, we obtained that 2% polymeric fiber inclusion gives again the highest results. It gives the best result in the flexural strength test. Scanning electron microscopy studies. The microstructure of polymeric fiber reinforced soil samples is examined by scanning electron microscopy with different magnifications. Here we have two different magnifications, and when we check these two images, we can see the granular aggregates, which are sand particles, and the smooth matrix is the expansive soil. And here we can also see the fibers within the soil mixture. And in the second image, if we look at from here, we can see the bridging effect of the fiber in the soil mixture, in the expansive soil and sand mixture. Conclusions. The experimental results showed that stabilization in areas of expansive soils as landfill liner or road subbase can be efficiently done using an available sand resource mixed and compacted with expansive soil, forming a stable structure, which can further be reinforced using a locally produced plastic waste. Incorporation of such materials in soil mitigation is a favorable technique, also offering an opportunity for recycling and non-biodegradable wastes. References. I prepared this presentation by using my and Professor Dr. Bilses' publication, and all the references that I mentioned are available in this article. I also mentioned the ASTM standards because all of the experiments were done according to the ASTM standards. Thank you very much for listening my presentation, and also I would like to thank to the organizers of this symposium.